Hi, welcome back to the Cuzzy Sound channel, and this time round we're looking at where I've got to with my clock divider little kind of project. I'm trying to understand how to put together a very simple clock divider. Last time round we'd kind of looked at the basic core of it, the 4017 decade counter. Before that we kind of started at the other end and looked at how to synchronize the main clock input and the output from the decade counter. And so I looked at using a twin transistor AND gate so that you kind of matched the output when you got both clocks synchronized together. That's when you got the output. That was the AND, so you got the clock and the counter. The end of that video I said I would put a circuit together with the AND gate on the end of the clock divider. There's a circuit. I put it together. You know, the switch. If you get close in, you can see you've got the decade counter at the bottom and the two transistors forming the discrete AND gate at the top, and I wired it up. Didn't quite get in practice what I thought I would get in theory. Yeah, the good old theory into practice doesn't always go. In one orientation where depending on how I wired up either the main clock or the output from the counter to the two logic inputs on the AND gate, I either got the clock output from the divider, I either got it firing on every clock input, i.e. not dividing, or it gave me an output which basically sounded not very different, if at all, from what I got when I just used the 4017 decade counter on its own. So yeah, I abandoned that one. I went back and did a little bit more research to look at some theory, and that led me to the U-Synth clock divider design. And in that design they use a twin diode AND gate, and so a little bit more research and decided to find out how a twin diode AND gate worked and whether I could use that in my own simple clock divider. So yeah, this is kind of a little bit more about learning about basic electronics than anything else. So let's have a look at the U-Synth schematic layout and look at how you can build an AND gate with two diodes. Here we have a section of the schematic for the U-Synth clock divider. I'll put a link in the description for the whole article, and you can see the full schematic and actually read the theory behind how their clock divider actually works. But for us, we're interested in this blue square here, which is the discrete AND gate created by two diodes. So what makes it an AND gate? Well, we have a voltage input coming through a resistor and connecting to both anodes, both plus sides of the diodes, and then the output from your AND gate comes from this same junction. In this case they're going through what's basically a voltage divider to drive the base of this transistor, which disappears off and lights up a diode. The way I'm going to light up a diode when we see the breadboard layout is I will have a current limiting resistor and then an LED connected between the end of that resistor and earth, which just means that we'll be able to see the logic function in action as the LED lights up. The cathode end, or the negative end of the diodes, form each of the two inputs on this 2-input AND gate. So these are the things that you will check for being either at a logic high, logic low, 0 or 1. In our case, the logic low will be ground and the logic high will be whatever this rail voltage is. So these are connected to a clock in, goes to this diode, and then the output from the decade counter goes to this diode. So if the clock input is at 0 volts, then this is at logic low. If the output is at 0 volts, then this is at logic low. So on an AND gate, you've got to have both at logic high to get an output. So if they're both at logic low, then the output is logic low or 0. So 0, 0 gives you 0. The reason being is that this voltage, when these are at 0 or grounded, they will conduct. So you will get a flow, because this is the higher potential. If this is always, we're supplying it with essentially logic 1, so that it will allow it to flow because there is a potential difference between what we're putting in and the state of these. These are both at ground, current flows. If one of these goes high, so this now is at the same voltage as this, then because there is no potential difference between the anode and the cathode, current will not flow through this diode. But if this one is still at ground, then there is a potential difference and current will flow, so it will go in that direction, so you won't get an output here because it's all going through the diode. And if we reverse that, this one is high, so this is at the same voltage, and this one is grounded, then current will flow through that one, so you won't get an output. But if both the logic inputs are high, so the cathode on both the diodes is at the same potential as the anode, there is no potential difference, current cannot flow in that direction, so it will flow in this direction because this will take it back down to a logic 0, so there is a potential difference on this side. So when that is high and that is high, it matches the high that we've already preset at this end, so the output here will be high because this is how we get the current flow. So there you go. That is how a 2-diode AND gate actually functions. Well, or at least that's the theory. It's all about whether there is a potential difference across the diode determining which way this current that we're putting in will flow. Okay, let's have a look at the breadboard and test that theory out with an actual circuit and have a look at LEDs lighting up. This is the breadboard circuit. Difficult to see because I haven't got a great close-up, but these are the 2 diodes. The stripe is the cathode end, and so they're going to separate tracks on the breadboard. The non-stripy end is the anode, and they both go to the same track, which then goes through this resistor to the positive supply rail. So if we think back to the U-Cinch diagram, we saw that the power was coming in here, going to both anodes of the diodes, and then the cathodes were each of the inputs. So these two are going to be our logic gate inputs. Coming from that same junction on the schematic, it went off to the voltage divider and the transistor. In our case, I've got a current limiting resistor and I've got an LED, and then the other end of the LED is down connected, and I plug it in down to the negative supply of the battery, or you can consider it as being sort of ground if you want, for the purpose of our logic. So we've got, so in this case, this rail will be logic high, and this rail will be logic low. Okay, and to kind of make it work, I'm going to connect it just to a battery pack. So if I take the input from one of the logic gates and connect that down to logic low, or the negative terminals on our system here, and take the input of the other one and put that one down to logic low. So what I've got here is I've got both so we've got supply going in to the anodes, and then we've got the logic inputs on the diodes, both at logic 0 or ground. If I connect, because my hand's in the way, but basically I've just connected power up, we've got nothing coming out of the output. Our little LED is not lit. So if I take one of the inputs and put that to logic high, nothing happens. Our little diode is still not lit. Put that back to logic low, put the other one to logic high, still no output. Now if I put them both at logic high, oh, the diode has just lit up when I've taken that one out. So that's it grounded, but I've not put it to logic high. If I do put it to logic high, the diode will stay lit. So why, when I've just not got it connected at all, do I actually get a logic output? Well, if you think back to what we said about it's all about the flow of current, all about there being a potential difference, when I've got the cathode of my diode, so this pink cable here is connected to the cathode on this diode, when I've got that cathode at ground, there is a potential difference between what's coming in here, and so current is going to flow in that direction. If I, and in this case the other one is at supply rail, so there is no potential difference there. But if I unplug that, what's actually happening is this input is now floating. The reality is that there's actually a resistance there, but the resistance is very, very high. It's the resistance measured across the air, across the atmosphere. But what it still doesn't do is, because it is such a high resistance, current can't flow in that direction, and therefore the current flows through the lower resistance path in that direction. So this is why it really is not good practice in logic circuits to leave inputs or outputs floating. So there we go, ground it, so we've got high on that one, low on that one, no output, high on that one, high on that one, output. But if I leave either of them floating, or even both of them floating, we get an output, because the resistance at this end is so high that current still cannot flow in that direction, so it has to go to the output. So if you just left your logic gate inputs floating, you're going to get an output on an AND gate. Now that could be important when we start and look at circuit design and looking at kind of, are we getting true logic states, you know, a 0 which is a ground and a 1 which is a matched voltage. Is that what we're actually getting on our logic gate? Because if we're not, we may not get the result in the output that in theory we are looking for. Well, that's the theory, and the theory tested out on the breadboard, and yeah, it sort of works. So once again, let's put theory into practice and build a circuit. So here it is. This time around I've put it onto a panel. So I'm not sure. Yeah, there we go. So this here is the basic 4017 decade counter on its own circuit board. So that's the very simple one that was dangling from wires on the modular last time round. If I tilt this over the other way, you can see that that is essentially the 2 diode AND gate, which is now wired in pretty much the same configuration as what they've got on the U-Synth module. And so I've got kind of, that's a bit close, got kind of the front end of the panel. So you've got the trigger input and an output. We've got the control for the switch for changing the reset loop time, i.e. the clock division. I've got on this side that allows me to switch in or out the AND gate circuit, and then on this side I've got a reset button. What I will say is that although I've ended up with something which is quite useful, I've also ended up with something which is probably again not quite what I expected in practice, given what I got in theory. But as I said, this video is more about understanding some more of the basic electronics behind AND gates. So I'm going to save the demonstration of the theory into practice for the next video, when what I will do, I'll have that panel in the Project 12 modular, I'll fire it up, and we'll start and listen to what it sounds like when you start wiring it into the rest of the modules and playing around with clock division. But yeah, I'll do another video on that. So this one, really, this has been a bit of theory. So hope you learnt something. I'm certainly learning a lot as I work my way through this. But yeah, you know, if you want to have a play around with logic, then yeah, well, have a go. Build your own little diode, or even the transistor AND gates, and make lights blink and things. It's just a bit of fun.